Okay, the next one is very, very important. I think if you are into statistical signal processing, you kind of encounter this very often. It's called the Gauss Markov process. Okay, heard of it?
No, sir.
Anyone? No. This is called. Let's look at an example of a Gauss Markov process. So essentially, again, this is a stochastic process. X of n belonging to z plus. Okay, that means 0 included. Okay, so I'm going to define this as follows: x of n plus 1 is equal to alpha times x of n. Alpha is a fixed number plus w of n. Okay, and n belongs to z plus, and x of 0 is 0. Okay, I should also describe what w of n is. So w of n, so w of n is an IID. What happened? Okay. Hey. Okay. I'll write here. So w of n. Okay. It's IID. Okay. With Gaussian 0 mean. Okay. And variance, let's say sigma square. Okay. This is the Gauss Markov process. Okay. Is that fine? So I can, if you are into signal processing, I can write this in a slightly different fashion. So it's almost like giving W of n. So there is some noise. Okay, I'll just add the noise with the delay, right? So this is the delay, and this is x of n. And all that I do is when I delay it, I'll multiply it by alpha. Okay, this is how it looks like, right? You delay it, multiply by alpha, and add it to w of n to get x of n plus 1. Okay, and keep doing that. So this is how you get it, but now I need to see what is the mean of this process. So let's look at what will be x of n. I'll write it recursively what this x of n is. X of n would be something like this: w of n minus 1 plus alpha times w of n minus 2 plus and so on. The last one would be alpha of n minus 1 w of 0. Okay, so this will be x of n. How did I write this? Well, recursively, alpha into x of n. X of n is alpha into x of n minus 1 plus w of n minus 1. So keep doing that, you will get it. Okay, so this implies the mean of x, right? The mean process is 0 because it's the sum of Gaussian IID random variables with 0 mean. Okay, what will be the covariance, right? So let's look at the covariance now. So expected value of x of n times x of m. So what I will do is okay, so let's look at this. So if I just do this, right? Okay, so x of 1 times x of 2 is same as x of 2 times x of 1, right? So what I will do is I'll slightly modify the way I'm going to write this. I'll just write n plus m. Okay, because if 1 is greater, then I can just commute it and then write it as x of n times x of n plus 1. Okay, so now okay, I'll give this as homework. I think even the textbook he doesn't give you the solution, but this is how it looks like: alpha power 2n, or I'll do it divided by 1 minus alpha squared. So how do you write this? How do you how do you prove that this is true? Yes. Yes.
Sir, it will be like summation alpha square power n.
Hmm? See, x of n plus m, I can write it in terms of x of n, right? Do you agree? See, what is x of, okay, let's look at this as x of n plus 2. This is alpha into x of n plus 1 plus w of 1, right? Is that correct? That's the notation that I have used. Yeah, w of n. Okay, this is, sorry, n plus 1. But this is equal to alpha into alpha x of n plus alpha into w of n plus w of n plus 1. Okay. So now x of n times x of n plus 2 would be what? Alpha squared x squared of n, right? This is what we have. So essentially what ends up happening is that then alpha times x of n into w of n plus x of n into w of n plus 1. Okay. Now x of n depends on w of n and w of n minus 1 and so on, right? It doesn't depend on w of n plus 1. So they are independent. So when you take expected value, the expected value of w of n plus 1 is 0. Therefore we need not worry about this term, right? Only we need to worry about these two terms. So what is x of n? X of n, so I can write this as alpha squared x squared of n. I'll just, this is an example, so how you can generalize this. Alpha times x of n is what? Alpha times x of n minus 1 plus w of n. Is that correct? So I've written n plus 1 is the previous. Okay, so n plus 1 is the previous. X of n is x of n minus w of n minus 1. So x of n also, it doesn't matter. So this is what you get, because x of n and w of n are independent. So when you take expected value, this is what you get. But x squared, x of n is something that I already have written, right? So x of n is given by this. All that I have to do is square this, right? So what will be the square of this? This squared plus this squared and so on. It will all be the squares. Expected value will be sigma squared times 1 plus alpha plus and so on, alpha n minus 1. It's a geometric series. The cross terms will anyway will be 0. So you have a geometric term here, right? That's why you get 1 minus alpha power 2n by 1 minus alpha squared. There is an alpha power k because, oh, okay. So now this is expected value of this whole thing will be alpha squared times expected value of, it will have 1, well, there is no expected, so we can take the expectation out. I mean, you can take the expectation in and write this. Alpha power x of n is what? Alpha power n minus 1. So this is, well, into sigma squared. So this is alpha squared sigma squared times what? You get this geometric series, right? 1 minus alpha power n divided by 1 minus alpha, right? Is that correct? Yeah. Do you agree with this? Maybe check. I might have missed out some terms, but I think the flow is correct. Okay. I might have done some algebraic mistake in between, but otherwise the flow is correct. Is this fine? Yes.
Sir, alpha is
Yes.
always less than 1, sir.
Okay, that's a good question. So, what happens to alpha here, right? So, if alpha is not less than 1, in fact, the mod alpha should be less than 1, then these things make sense. Okay, as you increase m, right? Keep on increasing. So this is not alpha power k; it's alpha power m. Okay, as you increase m, this go down. This will go down to 0. That means the correlation from, for example, if alpha is 1, what is it saying? It's saying if you take a signal like this, right? And if you take, this is your time axis, and if you take a point here, okay, this is, let's say, t, and you take a point which is like t plus m, and this is m, right? As and when m increases, the correlation between x of t and x of t plus m will go down to 0. It becomes almost independent. So the interesting thing about this is I can sort of assume that this random variable and this random variable are independent. Okay, so that you can use those facts to prove some sort of a law of large number kind of a result. Even here, even if it's correlated, still I can prove because they are independent, approximately independent. So I can replace this by independent random variables. So and apply law of large number. So it sort of mixes well. It becomes decorrelated after some time. Okay, that is true provided alpha is less than 1. If alpha is equal to 1 or greater than 1, it is not true. Okay, is that okay? Any questions? Okay, so I think I'll just state what, maybe I'll do it in the next class. So there is something known as stationarity. So what it essentially means is that if you take a k points, okay, x of t1, x of t2, and so on, x of tk, of course it's jointly Gaussian, it has some distribution. But if you shift the entire thing by any tau, right, the distribution doesn't change. Then we say that this process is stationary process. Okay, it should happen irrespective of what k points you pick and irrespective of what tau is. Okay, that's called stationary. And we'll see what is the condition under which Gaussian process is stationary process. It turns out that you just have to the covariance function doesn't depend on 2 points u and v. It only, or t and tau, it depends on the difference. Okay, t minus tau or tau minus t. Okay, so that's called. Then we can use that to define what is known as white cell stationary for a general stochastic process. Okay, once we do that, we will see how to construct a new or a Gaussian process using IID Gaussian random variables. Okay, that's where we need. Okay, just to give you a prelude for that, which we'll see in the next class.